Hi, this is Mr. Mac. Now, we wanted to do a review of the sequences and series chapter for the test, and so I've created this page, and I'm going to create this video so that you can watch it if you wish. Now, they give us basically two types of sequences and series that we have names for. There are a lot of different sequences and series, but the two that we basically focus on in Algebra 2 are of two basic types. Now, one basic type is arithmetic. Now, an arithmetic sequence, it can be defined by saying to find a term in the arithmetic sequence, you take the term right before it, and you add some constant to it to get the next term. Now, a recursive definition of that would be any term, any nth term would be the n minus 1th term plus a constant d. Now notice a sub n and a sub n minus 1. What we want you to see when you think of a sub n and a sub n minus 1 is that a sub n is the term right after a sub n minus 1 in the sequence. Because if you think about it, n is the counting number that's right after n minus 1 in the counting numbers. So if we're saying if n was 5, for example, a sub n minus 1 would be 4, n minus 1 would be 4, so we would be saying the 5th term, a sub 5, is equal to the 4th term, a sub 4, plus the constant d. Now, I call this a recursive, or we call this a recursive definition, because you have to know each term from the first up to the term you want to know. If I said to you, for example, that a sub 1 was 7 and the common difference was 5, then you would know that the second term was 12, third term was 17. That wouldn't be too difficult. But what if I said, what is the 100th term? Well, to know the 100th term, you'd have to start by taking the first term to get the second, then take the second term to get the third, then take the third term to get the fourth, and so on and so forth, if you follow just the recursive definition. So mathematicians aren't really that fond of recursive definitions. There is, however, for arithmetic sequences, an empirical definition for the nth term of a sequence, and that is this one. A sub n is equal to a sub 1 plus n minus 1 times d. Now we call this an empirical definition because this one, if you know the first term and you know which the number of the term you want and the common difference, you can just plug those numbers into this formula and it spits out the term you want without having to look at all the ones in between. That's an empirical definition. And mathematicians believe that empirical definitions are better than recursive definitions. Or at least I do. I don't know. Maybe some mathematicians like the recursive ones better, but I don't know of any. Now, there is another way of looking at this. If we do a little math with this a sub n is equal to a sub 1 plus n minus 1 times d, it can become a sub n is equal to d times n plus a sub 1 minus d. Now, notice that this is a linear function. If n is the input and a sub n is the output, then d is something we know, a sub 1 is something we know. And so d functions like the slope for this linear function. Every time the number of the term you want goes up 1, the term goes up by d. And so d becomes the slope for this function. All right, now that that crisis has been averted, let's go back. I'm not quite sure where I stopped. I will just say that d is the slope of this linear function that gives you the arithmetic sequence. And if you think of this as y equals mx plus b, b would be a sub 1 minus d. So in other words, to find an equation for the nth term, you could also just say, if I know the common difference and I know the first term, then what I can do is I can say a sub n is equal to the common difference times n plus the first term minus the common difference for the constant. and that would give you an equation or a function that, if you restrict the domain to the natural numbers, will give you that arithmetic sequence. Now, the other thing that we do with arithmetic sequences is we sometimes ask what their sum is. Now, the symbol S sub n actually is thought of as mathematicians as the nth partial sum. If you have a sequence, you could sum, just say, the first term, which is pretty easy, or you could sum the first two terms, that would be S sub 2, or you could sum the first three terms, or the first four terms, and so each one of those would be a sum, and so S sub n would be the sum of the first n terms, and we call that the nth partial sum. Now, if you watched the video, you probably saw the story I told about Carl Friedrich Gauss when he was maybe 9, 10 years old, something like that, was asked to add the numbers from 1 to 100, and he discovered, kind of informally, the formula to sum the numbers of an arithmetic series, or to find the nth sum, partial sum of an arithmetic series, and it turned out to be how many terms you were adding divided by 2 times the sum of the first and the last. Remember, he was asked to add the numbers from 1 to 100, and so that's 100 over 2, or 50, times 1 plus 100, 101. So 50 times 101 was 5,050. And he wrote that answer down quickly and slammed the thing down on his desk. Now, it turns out that you were given another formula for the nth partial sum of an arithmetic series, and that was this one right here, n over 2 times 2a sub 1 plus n minus 1 times d. Now, both of these formulas are useful. Let me point out first that the second formula is actually just taking this first one, n over 2 times the quantity a sub 1 plus a sub n, and for a sub n, we're putting this value in, and so we have a sub 1 plus then another a sub 1, which is 2a sub 1, and then plus n minus 1 times d. Now, the reason that we have these two formulas is because they each require a piece of information that you're not required to know in the other one. If you know, for example, like Gauss, add the numbers from 1 to 100, he knew how many there were, he knew what the first one was, he knew what the last one was, and so this first formula works nicely for him. But if you're told, find the sum of the first 573 numbers that are like multiples of 3 or something like that, starting with, say 18, then you know the first term, you know how many you want, and you know the common difference, but you don't know what the last one is. Then this second formula will work better for you. So they're both useful at the appropriate time, so you kind of need to know which one is going to work for you. Now, that is pretty much all that there is to know about arithmetic sequences and series. Let me point out again, I don't know if I pointed out in this video, so I'm going to point out, maybe it's again, that if I asked you to add 2 and 3 and you multiplied them, that you should not be surprised if you get the wrong answer. So these formulas only work for arithmetic sequences and series. So before you apply these formulas, you've got to make sure that you're dealing with an arithmetic sequence or series. Don't apply them if it's not, because you will then obviously get what we refer to as the wrong answer. Now, the second type of sequence or series that we spend time with in Algebra 2 is a type called the geometric series. Now, in the geometric series, the recursive definition is that you take any term and multiply it by the common ratio to get the next term. So a sub n is always equal to a sub n minus 1 times r, where r is the common ratio. But once again, this formula can only really be used if you know all the terms up to that particular point. To know the second term, you have to know the common ratio in the first term. To know the third term, you have to know the second term. To know the fourth, et cetera, et cetera, et cetera. Now, an empirical formula, which would be nice for us to have, is available for geometric series sequences, and it is a sub n is equal to a sub 1 times r raised to the n minus 1. that n minus 1 is the exponents. Now, I don't have another formula for the nth term in a geometric series, but we do talk also about summing these series up. And in class, I derive for you this formula, that the sum of the first n terms of an arithmetic series is the first term, a sub 1, times 1 minus r raised to the n over 1 minus r. Now, this is the formula I like best, but your book probably also had a sub 1 minus a sub n times r over 1 minus r. And that's useful sometimes too, so it'd probably be a good idea to know both of those. Now, geometric series get to be more fun because in geometric series, if the common ratio applies qualifies in a certain way, then we can actually sum these things up to infinity. So if the absolute value of r is less than 1. Now, in your head, what that needs to say is if r is any value between 1 and negative 1. Now, that doesn't include 1 and negative 1. But if r is any value in between 1 and negative 1, then we don't really need to just stop at adding up the first n. We can add to infinity. Now, we don't usually put this infinity down there, but I did, just so you would know that's what we're talking about. We're adding all of the terms out to infinity. Usually, we just say s. And the formula for that is simpler than the formula for the nth partial sums of these geometric series. It's just the first term over 1 minus the common ratio. Once again, don't forget, you cannot apply this formula unless the common ratio qualifies. The common ratio has to be a number somewhere between negative 1 and 1. When it does, then we get all kinds of really wonderful things happening. This was a real problem for the Greeks. You've probably heard about Zeno and his paradoxes. He talks about not being able to walk out a door because first you'd have to walk half the distance to the door, and then from there you'd have to walk half that distance to the door, and from there you'd have to walk half that distance to the door, and you would keep this up, and there would always be more distance to walk to the door, and these are all positive numbers, and so he would say that can't be done because it's an infinite amount. Well, this is contradicting that, and here's the idea that each time you're walking half the distance you did before, so your common ratio is between negative 1 and 1, and so there is a limit to this sum, even though there's an infinite number of them, and so, and as you've experienced, you are able to walk out the door. Anyway, so now you know more than some of the Greeks did. The other thing that was talked about in the in this chapter was the binomial expansion. Now, the binomial expansion, there it is this is the basic binomial expansion. A plus b raised to the n is equal to the sum, k going from 0 to n, of n factorial over k factorial n minus k factorial times a raised to the n minus k times b to the k. Now, some students have asked, if there's a circle, well, I'll just make another one here. Some students have asked, can't I just use the Pascal's triangle? And yes, you can. What's I just circled in green here is the formula for the terms in Pascal's triangle. And so you can just use that as well. But this is a formula that it would behoove you to know, especially if you're going towards higher level math. And you will be expected to expand some binomials on this coming up test. Now, the one thing that's tricky about this is sometimes what they'll do, instead of saying give us the term that has the x cubed in it, that's pretty easy to do. But if they say what is the, say, the fifth term, then what you have to understand is that for the fifth term, since you start counting at 0, then by the time you get to 4, you've actually counted 5 things. Watch this with me. 0, 1, 2, 3, 4. Notice that when I said 4, I actually had the 5. So if they ask for the fifth term, you would set k 1 less than that, k equal to 4, and to use this formula. Now, I really haven't planned to show any examples of this, but this is just a general overview of what is going to be expected of you to know on the test. And there is a sample test online that you may download and work on and then come in and see me. And so I think we're done.